Welcome to Night Watch Observer. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world has gone quiet around you, I'm glad you found your way here. Maybe you're tucked under a blanket with the lamp still glowing soft in the corner. Maybe you're on a train, the window dark, the world sliding by somewhere out there in the night. Maybe there's a cup of something warm cooling beside you, half forgotten. Wherever you are, however you're listening, settle in. Get comfortable, there's no rush here, none at all. And before we begin, I want to say a quiet thank you. If you enjoy these slow journeys into the night, these gentle wanderings through the strange and beautiful things the universe keeps tucked away, a like and a subscribe really does help this little channel keep going. Small creators like me lean on that kind of quiet support more than you might think. And if you're already subscribed, if you've made the Night Watch part of your nightly ritual, thank you. Truly, it means a great deal. So while you're getting comfortable, I'd love to know, where in the world are you listening from tonight? What time is it in your corner of the dark? Leave it in a comment if you feel like it. I love imagining all of you, scattered across the globe, all of us awake or drifting in the same quiet hour. Now, I should warn you about something the way I always do. Tonight's subject is genuinely strange. It's one of those puzzles that once you really look at it, refuses to behave the way your common sense insists it should. So I'll do my best to keep my voice soft and my pace slow, to walk you gently through it like a guide, leading you down a quiet path by lamplight. But I can't promise the ideas themselves won't be a little bit thrilling. That's the bargain we make on these nights. I'll try not to make this so interesting it keeps you awake. But if it does, well, at least you'll have learned something lovely about the universe before morning. A fair trade, I think.
And if you drift off before we reach the end, that's perfectly fine. That's allowed. That's almost the point. The ideas will still be here, patient and waiting whenever you come back. You don't have to follow every thread. You don't have to hold every number in your head. You can let the words wash over you like the tide coming in and going out, in and out. And if your eyes grow heavy and the room goes soft around the edges, just let them close. The Night Watch is keeping watch.
You don't have to. So, let's begin, shall we? Slowly, one mystery at a time. I want you to picture something simple, something warm and familiar. Picture a campfire on a cold night. You know the feeling. The crackle of it. The way the flames lean and flicker. The orange light dancing across the faces of everyone gathered around. And you know, without anyone ever having to teach it to you, exactly how a fire works when it comes to heat. The closer you lean in, the hotter it gets. The flames themselves are the hottest part. Hold your hand just above them and you'll snatch it back fast. But step away just a few feet back and the warmth fades. The air a little distance from the fire is cooler than the fire. The air a good distance from the fire is cooler still. This is so obvious it barely deserves saying. Heat radiates out from the hot thing and grows weaker the farther you go. That's just how the world works. That's how it's always worked in every kitchen and every campfire and every candle flame you've ever sat beside. Now I want you to imagine that this stopped being true. Imagine a campfire where the flames are hot, yes, but the air a few feet above the flames is not cooler. Imagine that air is hotter. Not a little hotter, hundreds of times hotter. Imagine the flames themselves glowing orange, sitting at one temperature, and then the empty air floating just above them blazing at something so fierce it could vaporize almost anything you placed in it. The fire would be the cool part. The space above the fire would be the inferno. You would back away from the flames and walk straight into something far worse. It makes no sense. It feels almost like a riddle or a trick or a mistake. And yet, this is real. This is happening right now on the nearest star to us. This is happening on the sun. Our sun, That great golden lamp that warms our days and ripens our harvests and has been the steady heartbeat of life on Earth for billions of years, is hiding a paradox so strange that the cleverest minds who study it have wrestled with it for the better part of a century. The puzzle has a name. Scientists call it the coronal heating problem. And tonight, slowly and gently, we're going to walk all the way into it together. We're going to understand why it's so baffling. And then, and this is the part I love most, we're going to follow the trail of clues that in recent years has started to crack this old mystery open, because this isn't a story about scientists throwing up their hands and giving up. Far from it. This is a detective story. And the detective, as you'll see, is a spacecraft built from a block of carbon foam smaller than you'd imagine that flew straight into the fire to find the answer. But I'm getting ahead of myself. Slow down, we have all night. Let's start with the numbers, because the numbers are where the strangeness first bites. And don't worry, there's no need to memorize any of this, no test in the morning. Just let the shapes of them settle in your mind. The surface of the sun, the part we actually see, the glowing golden face of it, has a name. It's called the photosphere. That word simply means the sphere of light, and that's exactly what it is. It's the layer that emits the light that travels all those millions of miles across space to land softly on your skin on a summer afternoon. The photosphere is hot. Of course it's hot. It's the surface of a star. It sits at a temperature of roughly 5,500 degrees Celsius. Let that number sink in for a moment. 5,500 degrees, hot enough to vaporize any metal you could name, hot enough to turn iron and gold and tungsten into glowing gas. There is nothing on Earth, no furnace, no forge, no volcano, that comes anywhere close. 5,500 degrees is the temperature of the burning face of our star. That, you would think, must be the hottest part of the whole arrangement. And now look just above it. Just above that blazing surface, floating in the thin atmosphere of the sun, is a layer called the corona. The word comes from the Latin for crown, because that's what it looks like. A pearly, ghostly crown of light. We'll talk later about why you can almost never see it. But for now, just hold on to its temperature. The corona, that wispy outer atmosphere hovering directly above the 5,500 degree surface, is not cooler. It is not a little hotter. It reaches temperatures of 1 to 3 million degrees Celsius. In some active patches, it climbs even higher. Sit with the size of that gap for a moment. The surface is 5,500 degrees. The atmosphere just above it is 1,000,000 degrees or more. That's not twice as hot. It's not 10 times as hot. The corona is somewhere between 200 and 500 times hotter than the surface lying directly beneath it, 200 to 500 times. It's our impossible campfire made real. The flames sit at one temperature and the air floating just above them blazes hundreds of times hotter. And these two layers are not far apart. The corona is right there, hovering directly over the photosphere, like the warmth above the fire. The cool part is the surface. The inferno is the air above it. Now, when you first hear something like this, a sensible part of your mind tends to reach for the easy explanations. Maybe it's a measurement error. Maybe someone read an instrument wrong. Maybe it's one of those things that sounds dramatic, but dissolves the moment an expert looks at it properly. And that's a perfectly reasonable thought to have. So let me close that door gently, because the strangeness only deepens when you do. This isn't a mistake. This temperature has been measured again and again across decades by many different methods and many different instruments. The corona really is 1,000,000 degrees and more. The surface really is 5,500. There is no measurement error hiding here to rescue our common sense. The riddle is real, and it has been sitting there glowing quietly in the sky for a very long time. So if it's real, why is it such a problem? Why don't scientists just shrug and say, well, that's just how the sun is, because of a rule, one of the deepest, most reliable rules in all of physics. A rule so dependable that you obey it every single day without ever thinking about it. The rule is this: heat flows from hot things to cold things, always, never the other way around. This is part of what physicists call the second law of thermodynamics, and you already know it in your bones, even if you've never heard the name. When you set a hot mug of tea down on a cold table, the heat flows out of the tea and into the table and the air until eventually the tea goes cold. The tea never gets hotter by stealing warmth from the cool room around it. That would be absurd. You've never once seen a cup of cold water spontaneously start boiling while the warm kitchen around it grew chilly to feed it. It simply doesn't happen. Heat moves downhill from hot to cold, the way water flows downhill from high ground to low. It does not flow uphill on its own. Now bring that rule back to the sun. We have a surface at 5,500 degrees. We have an atmosphere just above it at over 1,000,000 degrees. If heat was simply flowing out from the surface, the way it flows out from a campfire, then the atmosphere above should be cooler than the surface. It should be the cool air above the flames. Instead, it's hundreds of times hotter. The heat appears to be flowing uphill. Energy seems to be moving from the cooler surface into the hotter atmosphere, growing more intense as it climbs, in flat defiance of one of the most ironclad rules we know. And here's the thing, the rule isn't actually being broken. The second law of thermodynamics is not wrong. The sun is not cheating physics. But the only way both things can be true at once, with the rule holding firm and the atmosphere blazing hotter than the surface, is if something else is going on. Something is carrying energy up into the corona and dumping it there directly. Not by simple heat flowing from the surface, not by radiation or conduction, the way warmth comes off a fire. There has to be a separate, hidden source of energy, some other process entirely, reaching up into that thin outer atmosphere and pouring energy into it from the inside. Some hidden engine, some secret mechanism, something we cannot see, doing the heating in a way that has nothing to do with the ordinary spread of warmth from a hot surface. And that right there is the heart of the coronal heating problem. It's not just why is the corona hot, it's what is this hidden source of energy, this secret engine that reaches up past the cooler surface to set the thin air above it ablaze? Where is that energy coming from? What carries it? How does it get deposited so high up, so far from the surface, in defiance of everything our intuition tells us? That is the question. Hold on to it. We'll return to it again and again tonight, and slowly, piece by piece, we'll close in on the answer, because there is an answer beginning to take shape. And it's stranger and more beautiful than you might guess. But before we go chasing the hidden engine, I want to share with you a twist in this story that I find genuinely delightful. Because there's something hiding inside the word hot that, once you understand it, makes the whole picture even more wonderful. And it's the kind of idea that I promise you'll find yourself thinking about long after tonight. Let me ask you a question. If the corona is 1,000,000 degrees and a spacecraft were to fly straight into it, straight into that 1,000,000-degree atmosphere, surely it would be instantly destroyed, wouldn't it? Vaporized in a heartbeat, reduced to a puff of glowing vapor. That's what your instinct says, and it's a very good instinct. 1,000,000 degrees should annihilate anything. And yet, and here's where I have to ask you to trust me, because we'll come back to this in full later tonight. A spacecraft has flown into the corona. It flew into that 1,000,000-degree atmosphere, and it survived. Its instruments, tucked just behind a shield, stayed at roughly room temperature, about 30 degrees Celsius, cool enough that you could have rested your hand against them. How? How on earth is that possible? How can something fly through 1,000,000 degrees and stay as cool as a warm spring afternoon? The answer is one of the loveliest little secrets in all of physics, and it turns on the difference between two words we usually treat as the same thing: temperature and heat. We use them interchangeably in everyday life. We say something is hot, we say it has a high temperature, and we mean the same thing. It'll burn us. It carries a lot of warmth. But to a physicist, these are not the same idea at all, and the corona is the place where they split apart most dramatically. Here's the gentle truth of it. Temperature is a measure of how fast individual particles are moving. The faster the particles jiggle and zip around, the higher the temperature. When we say the corona is 1,000,000 degrees, what we really mean is that the individual particles up there, the tiny scraps of charged gas, the electrons and ions, are moving extraordinarily fast, frantically fast. Each one is racing around with enormous energy. So yes, in terms of temperature, the corona is genuinely, truly 1,000,000 degrees. That part is real. But heat, the heat you actually feel, the warmth that flows into your hand and burns you, heat depends on something more. It depends on how many of those fast-moving particles there are all together, ready to transfer their energy into you. And this is where the corona reveals its secret. The corona is almost unimaginably empty. It is a near-perfect vacuum. It is roughly 1,000,000,000,000 times less dense than the photosphere below it. Let me say that number more slowly because it's a hard one to feel. 1,000,000,000,000 times thinner. The thin, glowing surface of the sun is already a wispy thing compared to the dense water and rock we know. And the corona is 1,000,000,000,000 times thinner still. It is emptier than the very best vacuum we can create in any laboratory on Earth. Emptier than the most carefully pumped-out chamber a scientist has ever built. Out there in the corona, the particles are screaming along at 1,000,000 degrees of speed. But there are so vanishingly few of them that all together they carry almost no heat at all. Picture it this way. Imagine a single, tiny spark flying off a bonfire. That spark is glowing white hot. Its temperature in that fleeting instant is tremendous, but if it lands on your arm, it doesn't burn you, does it? You barely feel it. A flicker and it's gone, because it's only one tiny spark. It carries almost no actual heat, no matter how high its temperature, because there's so little of it. Now imagine the whole bonfire instead, thousands upon thousands of glowing embers, vast amounts of hot material, all radiating together. That will absolutely burn you because there's so much of it pouring its energy your way. Same kind of heat in each ember, wildly different amounts of total warmth. The corona is the single spark, made enormous and spread thin. Its particles are blisteringly fast, 1,000,000 degrees of temperature, but they are so few and so far apart that the total heat is tiny. If you could somehow hold an ordinary thermometer out there in the 1,000,000-degree corona, it would barely register. It would warm up only slightly because there simply aren't enough particles striking it to transfer much energy. A thermometer in a 1,000,000-degree atmosphere, reading hardly warm at all. It sounds like a contradiction, but it isn't. It's the difference between temperature and heat laid out for us in the sky. I find this so quietly beautiful. The corona is a place where the universe pulls apart two ideas we always assumed were welded together. It shows us that hot can mean two completely different things. That 1,000,000 degrees can, in a sense, feel cool. And it's exactly this strange split that lets a spacecraft fly into the fire of the corona and come out the other side with its instruments resting peacefully at room temperature. The few particles up there strike its shield and heat the surface of it considerably, yes, but there are so few of them that the warmth never builds up the way it would in a dense atmosphere. The temperature is 1,000,000, the heat is gentle, and that gap between them is the door through which our little detective spacecraft was able to slip straight into the corona to gather its clues. So already, you see, this puzzle has handed us two surprises, and we've barely begun. The first surprise, the atmosphere above the sun's surface is hundreds of times hotter than the surface itself, as if the air above a campfire blazed hotter than the flames, in apparent defiance of the most reliable rule in physics, which tells us a hidden engine must be pouring energy up into that outer atmosphere. And the second surprise, that 1,000,000 degrees doesn't mean what your instinct thinks it means, because temperature and heat are not the same thing, and out in the near-perfect vacuum of the corona, a blistering temperature carries only the faintest whisper of actual warmth. Both of these are true, both of these are strange, and both of them are only the beginning. Because here's what's been quietly happening, away from the headlines over the last decade or so. While the popular telling of this story tends to end with a shrug, it's one of the great unsolved mysteries and nobody really knows, the real story is so much more hopeful than that. The truth is that this old puzzle has been cracking open, bit by bit, clue by clue. Scientists have narrowed the hidden engine down to a small number of suspects. They've sent spacecraft closer to the sun than anything has ever gone before. They've caught on camera tiny flickering events on the sun's surface that may be part of the answer. And they've found something extraordinary woven into the sun's magnetic field. Sudden kinks and folds, places where the magnetic field abruptly turns and doubles back on itself, that may be the very fingerprints of the hidden engine at work. We're going to follow every one of those clues tonight, slowly, gently, in their proper order. We'll go back to the very beginning, to a time when scientists, staring at a single, mysterious line of green light in the sun's atmosphere, were so baffled that they did something rather wonderful. They invented a brand new element that doesn't actually exist, just to explain it. We'll meet the curious fact that the temperature of the sun's atmosphere doesn't simply rise as you go up. It actually gets colder first, dipping down before it suddenly rockets up past 1,000,000 degrees, across a layer so thin it would astonish you. We'll narrow the hidden engine down to two prime suspects, two competing explanations, and we'll come to suspect, as the scientists now do, that the truth may be that both of them are guilty. And then near the end, our protagonist arrives, a spacecraft named after a living man, the first ever to carry the name of someone still alive to see it fly, the fastest object human beings have ever built, fast enough to cross from New York to Tokyo in less than a minute. We'll watch it dive again and again toward the sun, sheltering behind a shield not much thicker than a paperback book, until at last it did what nothing had ever done before. It touched the sun. It flew into the corona itself. And inside that 1,000,000-degree atmosphere, it found the kinks in the magnetic field that may finally tell us where all that missing heat is coming from. But all of that is still ahead of us. For now, I just want you to hold on to the wonder of where we've arrived. Somewhere out there, 93 million miles away, our star is doing something that should be impossible. It's warming its own thin atmosphere to 1,000,000 degrees and more, hundreds of times hotter than its blazing surface, and it's been doing it quietly, faithfully, for as long as it has existed, long before there was anyone here to wonder why. The heat seems to climb uphill, the rules seem to bend, and yet the rules are not broken. There is simply something there we have not fully seen, some hidden engine reaching up into the dark with energy to spare. So take a slow breath wherever you are. Let your shoulders soften down away from your ears. Let the warmth of the blanket, or the gentle sway of the train, or the quiet of your room settle around you like still water. There's nothing you need to do right now except listen and drift and wonder. We have a long, soft night ahead of us and a beautiful mystery to wander through together, and there is no hurry at all. Now, before we go any further into the puzzle itself, we have to deal with something rather curious, because you might be wondering, if the corona is right there, a 1,000,000-degree crown of light wrapped around the sun, Why isn't it the most obvious thing in the sky? Why don't we simply look up and see it blazing? Why did it take scientists so long even to realize it was there, let alone to discover how impossibly hot it was? The answer to that question is its own small wonder, and it's where the real history of this puzzle begins. So let's wander there next, slowly, and see how this whole strange story first revealed itself to us, hidden as it was behind the glare of the very star it surrounds. But before that, let me say a quiet thank you for being here. This is a small channel, just a calm voice in the dark. And if you find these slow journeys soothing, a gentle like and a subscribe really does help it keep going. Small creators like me rely on it more than you'd think. And to those of you who've already subscribed, who come back night after night, thank you, truly. You're the reason the Night Watch keeps its light on. So tell me, if you feel like it, where in the world are you listening from tonight, and what hour has settled over your corner of the dark? It's a lovely thing to imagine all of us scattered across the globe, drifting off to the same strange story. Now, let's go back to that campfire for a moment, because it really is the heart of all of this, and it's worth sitting with. Picture an ordinary fire on a cold night. You hold your hands out toward the flames, and you feel the heat pour off them. Lean in closer, and it gets warmer. Pull back, and it cools. That's how heat behaves. It flows outward from the hot thing to the cooler things around it, spreading, fading, softening with distance. It's one of the most dependable rules in all of nature. Heat moves from hot to cold, never the other way, not on its own. A cup of tea left on the table cools toward the temperature of the room. The room never spontaneously warms the tea back up. You've felt this rule your whole life, even if you never named it. Now imagine standing at that same fire and discovering that the air a few feet above the flames was not cooler, as it should be, but hundreds of times hotter than the fire itself. Hot enough to make the flames seem cold by comparison. You'd think something had gone wrong with the world. You'd check your instruments. You'd assume you'd made a mistake, because that simply isn't how fire works. That isn't how anything works. And yet that is exactly, precisely what the sun is doing. Let me give you the numbers, because they're the kind of numbers that are almost hard to hold in your mind, and there's no need to memorize them. Just let them wash over you. The surface of the sun, the bright golden face we see, the layer called the photosphere, sits at about 5,500 degrees Celsius. That's already almost unimaginably hot, hot enough to vaporize anything we've ever built, hot enough that nothing solid could survive there for an instant. And then, just above it, in the thin glowing crown we call the corona, the temperature is not 5,000 degrees, it's 1 to 3 million degrees, million, not hundreds, hotter, not even thousands, hundreds of times hotter, sitting directly, immediately above the surface that's so much cooler, 200 times, sometimes 500 times. The flames, and then the air above the flames blazing far, far hotter than the flames could ever be. Sit with that for a moment. The coolest part of the fire is the fire itself. The furnace is calmer than its own breath. It feels, when you first hear it, like it must be a mistake. Like someone got the measurements backward, and for a long time, that's roughly how scientists felt too. Because if you think about heat the simple way, the campfire way, the cup of tea way, this should be impossible. Heat flows downhill from hot to cold. But here, it seems to be flowing uphill, gathering at the top, pooling in the thinnest, outermost layer, where by every ordinary expectation, it should be coldest of all. It looks at first glance like the sun is breaking one of the deepest rules in physics, the one that says heat won't climb from a cooler place to a hotter one all by itself. And here's the thing, that rule is not actually broken. It never is. Nature doesn't cheat. But when you see something that looks like it's breaking an unbreakable rule, there's really only one explanation left. There must be some other source of energy hidden working a way out of sight, pouring heat into that outer layer through a door we hadn't thought to look for. The corona isn't being warmed from below, the way the air above a campfire is. Something else is heating it directly from some engine we couldn't see. And finding that engine, understanding it, is the whole story we're drifting through tonight. But before we go looking for the hidden engine, there's a beautiful twist hiding in those numbers. And it's the kind of thing that makes the whole puzzle gentler, almost playful once you understand it. Because when I say the corona is 1,000,000 degrees, your mind probably pictures something ferocious. An inferno, a wall of fire so intense it would obliterate anything near it in a heartbeat. And in a way, yes. But also, strangely, no. Here's the secret. Temperature and heat are not quite the same thing. Temperature is really just a measure of how fast the tiny particles in something are moving. In the corona, the individual particles are moving astonishingly fast, and so by that measure they are genuinely, truly millions of degrees. That part is real. But heat, the kind of heat that warms you, that you could actually feel, depends on something else too. It depends on how many of those particles there are. And the corona is almost unbelievably empty. How empty? The corona is something like 1,000,000,000,000 times less dense than the surface beneath it. 1,000,000,000,000. It's thinner, far thinner, than the very best vacuum we can create in any laboratory on Earth. It is, by the standards of everyday matter, very nearly nothing at all, a vast, glowing, near emptiness. So imagine this. Imagine you could somehow hold a thermometer up into that 1,000,000-degree corona. You might expect it to melt instantly, to vaporize, but it wouldn't. It would barely warm at all. Because even though each particle that struck it is moving with tremendous blistering speed, there are so very few of them, so impossibly few, that they can hardly hand over any warmth at all. It's the difference between a handful of sparks flying off a grindstone, sparks that are genuinely thousands of degrees yet land on your skin and do nothing, and a whole oven full of slow, dense, steady heat that would burn you the moment you reached in. The sparks are hotter, the oven is more dangerous, high temperature, low heat. That's the corona, searingly, genuinely hot by the proper measure. And yet so thin, so sparse, so close to empty that it holds almost no heat at all. 1,000,000 degrees and barely warm to the touch. It's one of the loveliest contradictions in all of nature. And once it settles into place in your mind, the whole impossible thing starts to feel little less like a violation and a little more like a beautiful trick of definitions. So that's our paradox laid out gently before us. A surface at 5,000 degrees and an atmosphere above it hundreds of times hotter still. Heat that seems to flow the wrong way. A hidden source of energy we haven't yet named. And a crown of fire so thin it would scarcely warm your fingers. All of it true, all of it real, all of it waiting patiently for someone to come along and explain it. And there's something else worth knowing before we go looking for answers, something that shapes the whole history of this mystery and explains why it took us so long to even begin asking the right questions. The corona, that blazing 1,000,000-degree atmosphere, is almost entirely invisible to us. Not because it isn't there, not because it's small, but because the sun itself drowns it out. The photosphere, that churning visible surface glowing at 5,500 degrees, outshines the corona by roughly 1,000,000 to 1. 1,000,000 to 1. And so the corona, despite being far hotter, despite stretching outward for millions of kilometers into space, is simply overwhelmed, washed out, hidden behind a wall of brightness so intense our eyes can't separate one from the other. It's a little like trying to see a lit candle held up against the face of a searchlight. The candle is real, the candle is burning, but the searchlight swallows it whole. And so for most of human history, the corona existed without anyone really knowing it existed. The sun rose and set, ancient and indifferent, carrying its invisible crown above it, and nobody on the ground below could see it. There was one exception. One narrow window, a total solar eclipse. You've perhaps seen photographs, or maybe you've been lucky enough to stand in the shadow yourself. When the moon slides exactly in front of the sun, blocking that blinding photosphere, blocking all that searchlight glare, what's revealed in the sudden, eerie afternoon darkness is astonishing. A soft, pearly halo, silvery and delicate, reaching outward in long, structured streamers like the petals of some enormous cosmic flower or the flowing veil of something ancient and dignified. That is the corona. Visible to the naked eye only when the moon performs this extraordinary courtesy of getting precisely in the way. And for centuries, that was the only time anyone saw it. Eclipses are brief things, a few minutes at most. In those few minutes, astronomers scrambled, they drew sketches. Later, they pointed telescopes and cameras. And beginning in the 19th century, they pointed something new. Spectroscopes, instruments that could take incoming light and spread it into a rainbow, a spectrum, and read what was written there in the pattern of bright and dark lines. Each chemical element, each atom, leaves its own unique fingerprint in a spectrum. Hydrogen looks one way, sodium looks another, calcium another still. The spectroscope was the device that let us read the periodic table of the universe without ever leaving the ground. And when astronomers pointed spectroscopes at the corona during eclipses, they found something they couldn't explain. A bright green line. A specific, very vivid, bright green emission line sitting at a wavelength of 530.3 nanometers, glowing strongly from the corona. They also found a red line and a few others. But it was the green one that drew the most attention, the green one that refused to go away, the green one that sat in the spectrum like a quiet, stubborn secret. The problem was simple and bewildering in equal measure. Nobody could identify it. They checked it against every known element. They checked it again. It didn't match hydrogen. It didn't match helium, which had itself only recently been identified in the sun's spectrum in 1868. And notice how we know helium because of the sun, not from the Earth, but this new green line wasn't helium either. It didn't match iron, calcium, sodium, oxygen, magnesium, anything in the chemist's cabinet. It was a spectral fingerprint nobody had ever seen, and it was coming from the sun's corona. Scientists drew what felt at the time like a perfectly sensible conclusion. If the line matched no known element, then perhaps it was coming from an unknown element, a new element, one not yet found on Earth, one that existed in the sun. They gave this hypothetical new substance a name. They called it coronium, after the corona itself, and the name sat in the literature for decades, a placeholder, waiting for someone to confirm it or refute it. It's a cautionary tale that deserves a moment's pause because it shows how even careful, rigorous scientists can be fooled when they're right at the edge of what they know. In 1868, there had been another mysterious spectral line in the sun, also unidentifiable at the time, and the response had been exactly the same. A new element proposed, named helium, after the Greek word for the sun. And in that case, it turned out to be right. Helium existed. It was later found on Earth. The solar discoverers were vindicated. And so when the green coronal line appeared and resisted all identification, perhaps it was natural to reach for the same explanation. Another new element, another solar mystery, with a graceful naming solution. But coronium didn't exist. There was no coronium. And the green line had a much stranger story to tell. The answer began to emerge in 1939, when a Swedish astronomer named Walter Grotrian studied the coronal spectrum with fresh eyes and new atomic physics. And it deepened decisively in 1941, when a Swedish physicist named Bengt Edlén worked out the full solution and published it and changed the field permanently. What Edlén showed, with careful and meticulous calculation was that the mysterious lines, the green line, the red line, the others, were coming from iron. Ordinary iron, the same iron in your kitchen, the same iron in the ground beneath your feet. Not some exotic coronium, not some alien substance unique to the sun, but iron, the most prosaic metal imaginable. The catch was extraordinary. To produce those specific emission lines, iron has to be ionized. That means it has to lose electrons, the tiny particles that orbit the nucleus, stripped away by intense heat. A neutral iron atom carries 26 electrons. You can strip away 1 or 2 electrons with relatively modest energy, but the coronal lines weren't coming from iron that had lost 1 electron or 2. They were coming from iron that had been stripped of 9 electrons, what physicists call Fe9, iron in its 9th ionization state, all the way up to iron that had lost 13 electrons, Fe14, which was the very atom responsible for the bright green line at 530.3 nanometers. To strip 13 electrons from an iron atom requires an extraordinary amount of energy, the kind of energy that can only come from temperatures in the millions of degrees. This was the moment the coronal heating problem was officially born, not as a vague suspicion, not as an interesting curiosity, but as an iron-hard fact. If the corona was producing those lines, the corona had to be at temperatures of millions of degrees. There was no way around it. The spectral fingerprint was unambiguous, the atomic physics was settled, and the result was that an atmosphere sitting above a 5,500 degree surface was somehow, impossibly, at temperatures more than 100 times greater. The coronium placeholder was retired, the real element was named, and the real mystery, the far deeper and more troubling mystery, took its place. It's worth staying with Edlén's achievement for a moment, because it required something genuinely difficult. In 1941, the behavior of highly ionized atoms was still being worked out. The idea that iron could exist in such extreme ionization states that it could be stripped down to a bare-bones version of itself with barely half its electrons remaining was a relatively recent theoretical development. The atomic physics had to be built carefully before the astrophysical inference could be drawn. Edlén and Grotrian were doing something that required both exquisite experimental data from eclipse spectroscopy and a command of cutting-edge atomic theory. And they got it right. The green line at 530.3 nanometers, that vivid and stubborn signature, is still used today as a diagnostic of 2 million degree plasma in the corona. The same line whose identity it took decades to establish has never stopped being useful, so the corona is genuinely hot, not in some loose metaphorical way, not in some definition-dependent way, but hot in the full, precise, physical sense, in the way that only extreme temperatures can explain the atomic reality we observe. 1 million degrees, 3 million degrees in active regions, sometimes more, revealed first by a green light no one could explain, and then by a quiet Swedish physicist who sat down with the atomic physics and worked out what iron looks like when you take away 13 of its electrons. But here is where the story takes a turn that is easy to overlook, one that most accounts skip past too quickly, because most accounts jump straight from the temperature revelation to the question of why. And the why is important, the why is what we're here for. But there's something between the temperature discovery and the question of mechanism that deserves careful attention. Because it isn't just that the corona is hotter than the photosphere. It's how the temperature changes as you move upward from the surface. And that profile, the actual shape of how heat varies with altitude, is far stranger than most people realize. Let's drift upward together, slowly, from the visible surface. Imagine you could rise like smoke from the photosphere itself. From those 5,500 degrees of roiling, granulating, heaving plasma. The first thing that happens as you move upward is that it gets cooler. Not warmer, cooler. Moving away from the sun in the very lowest layers of the chromosphere, the temperature actually drops, down to roughly 4,000 degrees Celsius at its minimum, the chromosphere's floor, the lowest point in the sun's temperature profile. It's counterintuitive even before you get to the strange part. You'd expect things to cool as you rose from a hot surface, the way a room cools as you move away from a radiator, so that part feels almost reasonable. You're moving away from the source. The temperature falls, yes, fine, that makes sense. But then something happens that makes no sense at all. The temperature starts to rise again, slowly at first. Through the chromosphere, the layer above that temperature minimum, the temperature climbs back up. 10,000 degrees, 20,000 degrees. The chromosphere is a layer of its own, a region of roiling hydrogen plasma and magnetic complexity, and it's significantly hotter than the floor it sits above. You're already climbing a temperature profile that is going the wrong direction, rising as you move away from the source rather than falling. Something is adding heat here, somewhere, and we're not yet at the most extreme part. Then you reach the transition region. This is a place, or rather a zone, that deserves its name, because what happens there is one of the most violent and abrupt changes in the entire observable solar atmosphere. The transition region is extraordinarily thin, a few hundred kilometers in a sun that is more than 1 million kilometers across. A razor? A membrane? A boundary so thin that if the sun were the size of a basketball, the transition region would be about the thickness of a sheet of writing paper. And across that vanishingly thin layer, the temperature rockets. Not climbs, rockets, from around 20,000 degrees on one side to over 1 million degrees on the other. From 20,000 to 1 million in a distance you could cross on foot in a matter of hours if you could walk on plasma at the edge of a star. In the context of the solar atmosphere, it is essentially instantaneous. One moment, 20,000 degrees, the next 1 million. This is the heart of the paradox, the place where the violation of expectation is most acute. Because if you think of heat as something that flows from hot things to cold things, which is what thermodynamics tells us under normal circumstances, then this profile makes no sense whatsoever. The photosphere is the hot thing. The corona above is supposed to be cooler, receiving whatever heat trickles upward from the source and spreading it out across a larger and larger volume as you move away. Instead, the temperature plummets slightly, then rises again, then explodes across an almost impossibly thin boundary into temperatures far beyond anything the source itself achieves. The phrase people reach for is that heat flows uphill, that energy moves from cold to hot, from surface to corona, as if water were pouring uphill from a low valley to a high mountain. And that's the phrase that needs a little care because it's vivid and it captures the intuitive wrongness perfectly, but it also sets up a misunderstanding that's worth clearing up gently. Heat doesn't literally flow uphill here in the sense of simple thermal conduction going from cold to hot. That would indeed violate thermodynamics, and physics isn't broken. What's actually happening is something subtler, something that the whole rest of this story will explain. The corona isn't being heated by heat flowing up from the surface. It's being heated by a separate energy source, a non-thermal source, energy that is deposited directly into the corona without passing through the surface to corona thermal gradient at all.
Energy that bypasses the ordinary rules of heat flow because it isn't heat. It's something else. And that something else is magnetism. But let's not rush there quite yet. Let's stay a little longer with the profile, the shape of the thing, because it carries another piece of the mystery that's easy to miss.
The transition region's sharpness is itself part of the puzzle. Astronomers using instruments sensitive to ultraviolet and extreme ultraviolet light, the wavelengths that these hot layers emit most strongly, can map where the transition region sits and how sharp it is, and it is remarkably, stubbornly thin, a few hundred kilometers consistently. If the heating mechanism was something simple and diffuse, a gentle warming spread throughout the atmosphere, you'd expect the temperature transition to be gentler, more spread out. But it isn't. It's knife sharp. That sharpness is a clue. Whatever is doing the heating is doing it in a very specific place, at a very specific height, with remarkable efficiency. The energy isn't leaking gradually upward through the atmosphere, like warmth through a wall. It's arriving somewhere above the transition region and staying there, deposited in the corona directly without spreading smoothly through the layers below. And this is what makes the temperature profile, with its dip and its rocket-sharp boundary and its million-degree plateau, so valuable as evidence. It isn't just a strange fact to marvel at, it's a constraint. Every proposed mechanism for heating the corona has to be able to explain not just why the corona is hot, but why the photosphere is comparatively cool, why the temperature dips before rising, why the transition region is so thin and sharp, why the heat stays up in the corona rather than washing back down. Every proposed mechanism has to fit all of those shapes at once, and that, as you might imagine, is not easy. But here's something wonderful about all of this, something that gets lost when the story is told as pure mystery, as pure bafflement, as pure scientists don't know. The shape of the temperature profile gives us something to work with. The thin transition region, the sharp gradient, the high plateau, these are not just puzzles, they're data. And data, however strange, is what science is made of. Edlén's green iron line was strange data too, unexplained for decades, and then it became the key. So the paradox is real, and it is deep, and it has a precise shape. A surface at 5,500 degrees, a temperature dip to 4,000, a slow climb through the chromosphere to 20,000, a razor-sharp boundary of a few hundred kilometers, and then a volcanic leap to 1,000,000 degrees or more, sustained across the corona. Super ionized iron atoms, stripped of 9 to 13 electrons, glowing with the specific light that only temperatures of millions of degrees can produce. A hidden energy source that deposits its gifts directly into the corona, bypassing the surface, bypassing ordinary thermal flow. And for a long time, astronomers could see all of this, could measure it with increasing precision during the brief, extraordinary windows of total solar eclipses, and later with space-based instruments that could see the ultraviolet and extreme ultraviolet light the hot layers emit even without an eclipse. They could see the shape of the mystery with exquisite clarity. But what they couldn't see, what remained genuinely hidden, genuinely contested, genuinely open, was the mechanism, the what makes it happen, the actual physical process by which energy gets from the churning surface of the sun into the thin, hot, tenuous corona above. That question would take decades more to address. It would require spacecraft and instruments that didn't exist in Edlén's time. It would require a new generation of solar physics armed with ultraviolet eyes that can see in wavelengths blocked by Earth's atmosphere, with magnetometers sensitive to the precise geometry of the sun's magnetic field, with cameras fast and sharp enough to catch the small and fast and fleeting phenomena that might be doing the heating. And it would require, eventually, a spacecraft willing to go much closer to the sun than any probe had ever dared. But before we get there, let's sit for a moment with what Edlén and Grotrian gave us, because it's a gift that's easy to underestimate. They gave us certainty. In a field where so much was uncertain, where the corona was seen only in snatched eclipse minutes, where spectral lines could be misread and theories could wander, they gave us something solid to stand on. The corona really is hot. Not a measurement error, not an artifact of the instrument, not a misreading of the spectrum. The iron atoms say so plainly and unambiguously in a language of quantum physics that can't be faked. That certainty is the foundation. The temperature profile is the shape of the mystery, and the search for the mechanism is the next chapter, which is where things get genuinely, beautifully complicated. You see, once it was clear that the corona had to be hotter than the surface, And once it was clear that ordinary thermal conduction couldn't explain it, the question of what could explain it opened up like a landscape after fog lifts, a wide, complex landscape full of candidates and controversies and competing ideas, full of things that each seemed plausible from one angle and impossible from another. The Sun is not, after all, a smooth and passive object. Its surface is constantly in violent motion. The photosphere seethes with convection, enormous cells of rising hot plasma and sinking cooler plasma, churning and churning in a pattern that covers the visible disk with a texture that looks, from a distance, like the surface of a pot of thick porridge slowly boiling. These convective cells range from granules, a few hundred, to about 1,000 kilometers across, to what are called supergranules, the giant versions, each one perhaps 30,000 kilometers wide, vast, slow overturning structures that define the landscape of the photosphere and, crucially, play a role in organizing the Sun's magnetic field. Because the Sun's plasma is electrically conducting and because it's moving, it drags magnetic field lines with it. The motion of the plasma and the behavior of the magnetic field are deeply, inseparably linked in a way that doesn't happen with ordinary non-conducting gases. Plasma and magnetic field move together, are coupled together in a way that physicists call frozen-in field. The field lines frozen into the plasma like wires frozen into a block of moving gel. Wherever the plasma goes, the field lines go with it. And so all that churning convection, all that boiling and stirring of the photosphere doesn't just mix the plasma, it braids the magnetic field, it tangles it, it wraps it around itself and under itself and over itself in increasingly complex knots and coils, the way a ball of yarn is tangled if you set a cat loose on it for an hour. The surface convection is constantly working the magnetic field into tighter and more complicated geometries. That tangled field extends upward into the chromosphere and the corona. Magnetic field lines reach up from the surface into the hot, tenuous atmosphere above, connecting one part of the photosphere to another, arching up in great loops and arches that can span hundreds of thousands of kilometers. And when you look at the corona in ultraviolet light, in the light that only the hot plasma can emit, what you see is those magnetic arches made visible. Glowing structures, bright and elegant, tracing the geometry of the field above the surface. They're called coronal loops, and they're among the most beautiful structures in all of solar observation. And those coronal loops, those bright magnetic arches, are where much of the heating debate will play out. But there's something worth noticing before we get to the mechanisms themselves, something about the Sun's magnetic field that makes this more than an aesthetic observation. The magnetic field is the medium, it's the channel. Whatever energy is being put into the corona, it's almost certainly traveling there along or through or by means of the magnetic field, because the magnetic field is the thing that connects the surface to the corona. It's the bridge across the temperature gradient. Energy has to find a way to move from the churning, convective surface into the thin, hot atmosphere above. And in a plasma, in an electrically conducting medium saturated with magnetic fields, the field is the most natural pathway. All of which means that understanding coronal heating is, in large part, about understanding what happens to magnetic energy in the solar atmosphere, how it gets in, how it moves, how it is eventually converted into heat. And that's a problem that requires thinking about magnetism in a way that's quite different from everyday experience. Most of us encounter magnetic fields in their static form, a compass needle pointing north, fridge magnets holding up drawings, the pull between opposite poles. These are stable, static configurations, field lines sitting quietly and doing their job. But in the solar atmosphere, the field is not static, it's dynamic. It's being pushed and pulled and braided and tangled by convective motions below and by the complex history of the field above. It stores energy in its geometry, in its twists and knots, the way a compressed spring stores energy in its compression. And when the geometry changes, when two field lines that were being held apart by various plasma pressures suddenly reconnect, snap together, merge into a new configuration, that stored energy is released explosively in the form of heat and particle acceleration and light. This is magnetic reconnection, and it is one of the two great suspects in the coronal heating mystery. But we're getting slightly ahead of ourselves, because before we can describe the suspects properly, it helps to understand the geometry of the field more clearly. And it helps to appreciate how the supergranulation of the surface, those vast overturning cells each 30,000 kilometers wide, connects to what happens in the corona above. As the supergranules slowly churn and turn, they sweep the photospheric magnetic field toward their edges, the way water being stirred in a bowl sweeps leaves and debris toward the rim. The field concentrates at the boundaries between supergranules in a honeycomb network of brighter, more intensely magnetized regions. You can see this pattern in magnetograms, maps of the Sun's surface magnetic field, where the concentrated boundary regions of the supergranular network glow with magnetic intensity while the interiors of the cells are relatively quiet. And extending upward from those concentrated boundary regions, like grass growing through cracks in pavement, are structures called coronal funnels, regions where the magnetic field opens upward from the concentrated photospheric footpoints, fanning out as it rises, guiding plasma upward into the corona. These funnels are not uniform, not static, not simply open tubes. They're dynamic, constantly being pushed by the convective motions below, constantly interacting with neighboring field lines, constantly at the boundary between different magnetic configurations. And at those boundaries, something is happening. Something that the Parker Solar Probe, flying closer to the Sun than anything ever had before, would eventually find a way to show us. But all of that comes later. For now, let's rest where we are for a moment. We've come a long way tonight already, through eclipse shadows and spectroscopic mysteries, through the story of a fake element that turned out to be super ionized iron, through the surprising dip and rocket-sharp leap of the temperature profile. We've arrived at the magnetic field, the medium through which the corona's mystery is going to be solved, or is at least in the slow, careful, evidence-by-evidence process of being solved. There's something quietly wonderful about the fact that the corona's invisibility is what delayed the discovery for so long, that a million-degree atmosphere was hiding behind a surface a million times brighter, visible only in the brief, rare, beautiful accident of a total solar eclipse, and that when astronomers finally pointed the right instrument at the right light during one of those brief windows, what they found was a single green line, unexplained, sitting in the spectrum like a word in a language nobody could read yet. Walter Grotrian in 1939, Bengt Edlén in 1941. Two scientists sitting with tables of atomic transitions, with spectral measurements taken during eclipses, with the new quantum physics of highly ionized atoms. And between them, they cracked it. Not with a rocket, not with a space telescope, not with supercomputers, but with careful thinking and hard-won data, and the willingness to follow an atomic physics argument wherever it led. They followed it to iron, and iron led them to millions of degrees, and millions of degrees led to a mystery that a spacecraft would eventually fly directly into, behind a shield the thickness of a paperback book, to find what was hiding there. That spacecraft is still out there, even now, as you lie in the dark, swinging its orbit closer and closer to the Sun on each successive pass, recording magnetic fields and plasma velocities and particle energies in a place no instrument had ever been before. Each orbit a little tighter, each approach a little closer, each pass carrying it deeper into the corona, past that Alfvén critical surface where the Sun's magnetic field takes over from the solar wind into the very zone where the heating happens, or at least where a significant part of it might happen. But what exactly is it looking for? What are the two main suspects described not in jargon but in plain physical terms? How does Alphen waves differ from nanoflares, and what would it actually mean for one or the other to be heating the corona? Those are the questions that deserve their own slow, careful space, their own unhurried walk through the physics. And that's exactly where we're going next. So if you're still with us, somewhere in your warm corner of the night, that's wonderful. There's no need to track every detail. You can let the picture of the magnetic field, the corona, the tangled field lines rising from the boiling surface, you can let that picture settle gently and carry it forward as we go. We know the corona is hot. We know the temperature profile has a strange and specific shape, cooler first, then hotter, across a knife-edge boundary. We know that iron atoms, stripped of 13 electrons, are doing the honest work of telling us how hot. And we know the energy has to come from somewhere, has to travel through the magnetic field from the churning surface to the thin, bright corona above. The shape of the mystery is clear. The candidates are waiting just ahead. And somewhere out in the dark, the Parker Solar Probe is still falling toward the sun, patient and silent and extraordinarily fast, carrying its questions and its instruments into the place where those answers might finally be found. So let us begin with the first suspect. Imagine plucking a guitar string. You stretch it taut, give it a flick, and what travels down the string is not the string itself moving from one end to the other. What travels is a wave, a ripple of motion, energy passing through the medium. The string vibrates, the wave runs along it, and if you could somehow convert that motion into heat at the far end, you would have transferred energy from your fingers all the way to the opposite peg without moving a single atom of the string the full distance. The wave does the carrying, the wave is the messenger. Now imagine a magnetic field line, a single invisible thread of magnetic force anchored in the churning, boiling surface of the sun, rising upward through the chromosphere, through the thin, violent knife edge of the transition region, and out into the corona above. That field line, like the guitar string, is under a kind of tension. Magnetic fields carry tension, and the surface of the sun, the photosphere, is not still. It is ferociously, constantly, violently in motion. Granules of plasma, each one roughly the size of a continent, rise from below, swell upward in a great bubbling convection, spread out at the surface, cool slightly, and sink back down, all of it in a continuous churning cycle that never, for a single moment, stops. Every time one of those granules rises and spreads and sinks, it jostles the magnetic field lines rooted in it. It shakes them. It flicks them sideways, the way a hand flicks a stretched rope. And when you shake a magnetic field line, you launch a wave that travels upward along that line at a speed that has its own name, the Alfvén speed, after the Swedish physicist Hannes Alfvén, who first described this kind of wave in 1942. These are Alfvén waves, magnetic vibrations. Ripples of energy propagating along the field lines, up through the chromosphere, up toward the corona, carrying the kinetic energy of the boiling surface in the form of a wave that travels through the magnetic field the way sound travels through air, or seismic energy travels through rock. The principle is elegant, and, once you have the guitar string picture in your mind, genuinely intuitive. The sun's surface shakes the field lines. The field lines carry the shaking upward. The shaking, somewhere up in the corona, converts into heat. If the numbers work, if the waves carry enough energy and if they deposit it in the right place, you have your coronal heating. No mystery element required, no exotic physics, just waves on strings at the scale of a star. The question is whether the numbers do work. And this is where it gets both interesting and genuinely difficult. Alphen waves have been detected in the corona. That part is confirmed. Instruments on various missions, including Observations from NASA's Solar Dynamics Observatory, which has been watching the Sun in extreme ultraviolet and X-rays continuously since 2010, have seen the characteristic swaying motions of coronal plasma that Alfvén waves produce. The waves are real, they are there. But carrying energy from the surface is only half the job. The waves also have to deposit that energy. They have to actually dissipate to convert their mechanical wobbling into heat. And here the picture becomes more complicated because Alfvén waves in a perfectly uniform magnetic field, in a perfectly uniform plasma, are remarkably reluctant to do that. They are efficient carriers, which means they are also efficient travelers. They want to keep going, not to stop and turn into heat. Getting Alfvén waves to dissipate their energy to actually thermalize, to become heat, rather than just pass through, requires the right conditions. Turbulence in the magnetic field, variations in density, reflections that make waves collide with each other and break down into smaller scales where dissipation can happen. The theory of wave heating is not simply waves go up and heat things. It requires a more intricate cascade, and exactly how efficient that cascade is, in exactly which regions of the corona, remains one of the genuinely open quantitative questions. There is a picture here, though, one that current models favor. In the large open regions of the corona, the areas called coronal holes, where the magnetic field lines are not looped back onto the Sun, but extend outward into space in long open threads, Alfvén waves may be the dominant heating agent. These are the regions that produce the fast solar wind, the high-speed stream of charged particles flowing out from the Sun's poles and certain equatorial regions. The plasma there is more tenuous, the field lines long and open, and Alfvén waves can propagate outward efficiently, depositing some of their energy into the solar wind acceleration as they go. Some analyses suggest this is exactly what happens, that wave heating is the right answer for the open field regions, for the coronal holes, for the birthplace of the fast solar wind. But the corona is not all open field. Much of it, especially above active regions, the magnetically busy zones that produce sunspots and flares, and the vivid arching structures we call coronal loops, is characterized by closed field lines that rise from the surface, arc upward into the corona to heights of hundreds of thousands of kilometers, and then curve back down and reconnect with the surface somewhere else, like enormous glowing bridges of magnetic force and plasma. This is where the second suspect enters the story. Eugene Parker, the same Eugene Parker who predicted the solar wind in 1958 and spent years being told he was wrong before Mariner 2 proved him right in 1962, the same Parker, whose name is now carried by the spacecraft flying toward the Sun, published a paper in 1988 that proposed a different mechanism, not waves, something more like sparks. Parker was thinking about what happens to those closed magnetic field lines, the ones that form the coronal loops, over time. The surface of the Sun is churning constantly, remember? Every granule rising and sinking, every swirl and eddy in the convection beneath the photosphere drags the footpoints of the magnetic field lines sideways. One footpoint of a loop is here, the other is there, and the surface beneath them is moving in different directions at slightly different speeds, endlessly. The result, if you trace what happens to the field lines threading through that chaos over hours and days, is that they get braided. They get twisted around each other. They get kinked and knotted and tangled, the way strands of string tangle when you jam them in a pocket and pull them out again. Now, magnetic field lines under tension do not like to cross each other. When two field lines are pushed toward each other into contact, something remarkable can happen. They can break, they can snap, reconfigure themselves into a new, lower energy arrangement, and in doing so release the energy difference as a burst of heat and motion. This process is called magnetic reconnection. It happens in the Sun's corona constantly. It happens on a grand scale during solar flares, when enormous loops reconnect and release the energy equivalent of billions of nuclear weapons in a matter of minutes. But Parker's 1988 proposal was about the small-scale version, the everyday, continuous version, not the dramatic flare but the countless tiny sparks happening all the time. He called them nanoflares. Each one individually is tiny, billions of times smaller in energy than a full-scale solar flare. A single nanoflare would be nearly impossible to detect. It would be far below the sensitivity of any instrument we have ever built. It would be, in human terms, less than a whisper, less than a ghost of an event. But Parker was thinking statistically. He was thinking about what happens if the corona is full of them, if they happen everywhere and all the time, if the surface churning is always braiding and tangling and eventually snapping field lines in a constant, low-level, near-continuous storm of tiny reconnection events. Add them up. Add up billions of nanoflares happening every second across the entire surface of the Sun, each releasing a tiny burst of energy, and the total might be enormous. Might, Parker argued, be exactly the right total to account for the corona's million-degree temperature. The collective hum of a billion tiny snaps, each individually invisible, together loud enough to boil a star's atmosphere to 1,000,000 degrees. The idea was beautiful. It was also, for many years, frustratingly difficult to test. Because the individual events are below the threshold of detection, you cannot simply point a telescope at the corona and count nanoflares the way you count flares. What you can do is look for their signatures. A nanoflare depositing heat into a coronal loop should briefly raise the temperature of the plasma at that point, far above the already high average. It should create for a brief moment plasma at temperatures of 10 or 20 million degrees, hotter even than the already astonishing average of 1 to 3 million. And there are ways to detect that very high temperature plasma. It emits X-rays at specific wavelengths that are the diagnostic fingerprints of matter at extreme temperatures, and those wavelengths are different from what you see at the more ordinary million-degree level. So the hunt for nanoflares became the hunt for very hot plasma. In the corona, plasma that is too hot to be explained by steady, uniform heating, but that would make sense as the product of localized, impulsive nanoflare events. And the evidence is tantalizing. There are observations consistent with nanoflare heating. The Solar Dynamics Observatory, watching the corona continuously in extreme ultraviolet, captures the glowing arches of coronal loops with extraordinary clarity. Those loops, traced against the dark background of space, look almost alive. They sway and twitch and occasionally flare. They are the visible architecture of the active corona, and within them, embedded in that steady glow, there are hints of hotter, brighter, briefer events that sit well with Parker's 1988 picture. But hints are not proof, and for years this second suspect, the nanoflare, remained a plausible theory without a smoking gun. Then in 2020 something arrived that changed the texture of the hunt. Not a detection of nanoflares directly, but something that looked very much like their smaller cousins. Something that gave the whole idea a new and vivid face. In February 2020, the European Space Agency, in partnership with NASA, launched a spacecraft called Solar Orbiter. Like Parker's solar probe, it is headed for the inner solar system and the vicinity of the Sun. But Solar Orbiter is designed to do something slightly different. Rather than plunging deep into the corona as close as possible, Solar Orbiter is built to watch, to image, to observe the Sun's surface and lower corona with a suite of cameras and instruments that can capture what the surface actually looks like from close range, closer than any imaging mission before it. At its closest approaches, Solar Orbiter swings within about 42 million kilometers of the Sun inside the orbit of Mercury, and from there, with its extreme ultraviolet imager, it takes pictures of the Sun that we have never been able to take before. In 2020, during its first close pass, Solar Orbiter's extreme ultraviolet imager captured the Sun in extreme ultraviolet light, the wavelengths at which hot coronal plasma glows most brightly, and the images revealed something unexpected. Not the large-scale loops and active regions already familiar from the Solar Dynamics Observatory, but something smaller. Scattered across the entire surface of the Sun in their thousands were tiny bright points, brief, small-scale flashes of brightness, each lasting only a few minutes, each covering an area much smaller than a typical active region or a conventional flare. They were immediately given a name that reflects both their scale and their possible relationship to the larger phenomenon. They were called campfires. The word is apt. A campfire is not a flare. It is not a storm. It is a small, low, local thing, doing its modest job quietly in the dark. And these campfires on the Sun are small in the same relative sense, even if the scale in absolute terms is still enormous, even if each one covers an area that could swallow a small country. Compared to a solar flare, they are tiny. Compared to the whole Sun, they are barely a flicker. But there are so many of them, scattered everywhere, all across the surface, burning continuously like a field full of small fires that never go out. The question, and it is a genuinely open one, is whether these campfires are the visible face of nanoflares or something closely related, whether they are the slightly larger, just barely detectable end of the nanoflare population, the tips of the iceberg that Parker's theory predicted but never quite managed to make visible. If they are, and if the energy they carry scales the right way, they could represent direct observational confirmation of the mechanism that Eugene Parker proposed in 1988. Not the theory proven beyond all doubt, not yet, but a vivid piece of circumstantial evidence. A face on an idea that had been, for 30 years, faceless. The campfires from Solar Orbiter are at the center of active research. There are groups analyzing whether the temperatures associated with these events, the wavelengths they emit, the lifetimes, the spatial sizes, all fit the nanoflare model. There are comparisons being made with the predictions from simulations, with the models of how magnetic reconnection on small scales should look when observed from this distance and with these instruments. The answer is not yet definitive, but the direction of travel is clear. Solar Orbiter caught something real, something that was there all along, but that we simply had never been close enough to see. And in science, being able to see a thing for the first time is often the step that changes everything. Solar Orbiter is doing something else remarkable as well, something that no mission before it has managed. It is tilting its orbit. Slowly, over successive close passes using Venus for gravity assists, Solar Orbiter is raising the inclination of its orbit, tipping it away from the ecliptic plane, the flat disk in which most of the planets orbit the Sun, and angling it upward toward the Sun's poles. The reason matters enormously for understanding the heating problem. The Sun's poles are the seat of a completely different magnetic structure. The fast solar wind streams predominantly from polar coronal holes, the large open-field regions near the poles where field lines extend outward rather than looping back. The global magnetic field that drives the solar cycle, the 11-year rhythm of activity and quiet, originates in the dynamo processes happening at and beneath the polar regions. And yet, we have never seen the Sun's poles. Every mission, every telescope, every observation so far has been made from the ecliptic plane, staring at the Sun from the side, seeing its equatorial regions clearly and its poles only obliquely, distorted by perspective, like trying to read a book held at arm's length and tilted away from you. Solar Orbiter is the first mission designed to look down toward the poles. Not all the way, not yet, but progressively over the coming years, the inclination will increase, and for the first time we will have images of the Sun's poles taken from an angle that actually shows them. And when we do, we will be looking directly into the source regions of the fast solar wind, into the roots of the global magnetic field, into the places where coronal holes are born. For understanding which mechanism heats the corona in open field regions, those images are likely to be transformative. So now there are two suspects, sitting side by side, wave heating and nanoflare reconnection. Two mechanisms, both real, both operating within the same domain of solar physics, both supported by evidence, and yet still competing in the sense that their relative contributions, who does more of the heating, in which regions and by how much, is not yet fully resolved. This is the honest state of the science, and it deserves to be described honestly. But here is where the story gets more interesting than a simple coin flip between two theories, because the evidence that has accumulated not just from Solar Orbiter and the Solar Dynamics Observatory, but from a broader picture of how the Sun's corona behaves in different regions, is pointing toward something more nuanced than a single correct answer. It is pointing toward what you might call a both-and resolution, not wave heating or nanoflare reconnection. Wave heating and nanoflare reconnection, in different places doing different jobs in different proportions. Consider the corona's geography. It is not uniform. A full disk image of the Sun in extreme ultraviolet shows a wildly varied surface. There are bright active regions, magnetically complex and energetically intense, clustered near the equator, especially during periods of high solar activity. There are the long, elegant arches of coronal loops stretching over those active regions, glowing against the darkness. And then there are the coronal holes, the darker patches, cooler and less dense in appearance, where the field lines are open and the plasma simply flows away outward into the solar wind rather than being trapped in loops. These two environments, the closed field active region with its coronal loops and the open field coronal hole, are very different physically. The closed loops are high-density, magnetically constrained structures where the plasma is trapped, and braided field lines build up stress over time. The open field coronal holes are more like vast magnetic chimneys, with the field lines extending outward and the plasma flowing along them and away. In the closed loops of active regions, the conditions are exactly right for nanoflare reconnection to dominate. The constant footpoint motions of the churning surface continually braid the anchored field lines. The loops are long and stable enough for the braiding to accumulate. When the field lines eventually snap and reconnect, the energy is deposited directly into the loop plasma where it is trapped. The Solar Dynamics Observatory images of these loops, with their subtle flickering and their temperature variations that hint at localized impulsive heating events, are consistent with a corona dominated in these regions by nanoflare-like reconnection. And the campfires that Solar Orbiter is seeing may well be the direct small-scale manifestation of exactly this process, the magnetic reconnection happening at the smallest scales we have yet been able to image. In the open field coronal holes, the picture looks different. The field lines there extend outward for enormous distances. The plasma is not trapped. What you want in this environment is not a mechanism that deposits energy locally into a closed loop, but one that can carry energy upward along the field lines and deposit it gradually as the solar wind accelerates outward. Alphen waves are very well suited to exactly this job. They travel along open field lines efficiently, they interact with the solar wind plasma, they can deposit energy gradually over a large range of distances, and there is observational evidence from multiple missions of Alphen waves propagating outward through coronal holes and the nascent solar wind. The picture that is emerging, and while it is still being refined and the quantitative details remain active research, the broad outlines are increasingly clear, is a corona heated by two mechanisms simultaneously, each dominating in its own natural habitat. Wave heating in the open field regions, nanoflare reconnection in the closed field loops. The corona has two faces, and each face has its own heat source. The question is no longer which one is right. The question is understanding the details of each, the energy budgets, the spatial distributions, the temporal patterns, the exact physical processes by which waves dissipate and by which reconnection events initiate and terminate. Those are the remaining questions, hard and specific and quantitative, the kind of questions that require data from inside the corona itself. Which brings us back to where we started, or rather forward, to where the story truly catches fire. Because the emerging consensus about two mechanisms operating in different regions is compelling and probably broadly correct, but compelling and broadly correct, built from observations made at a distance, from spacecraft still outside the corona, watching with extraordinary instruments from what is, in solar terms, still a long way away, is not the same as going there. Not the same as crossing the boundary, descending into the environment where the heating actually happens, and recording what the magnetic field, the plasma, the waves, and the reconnection events actually look like from the inside. And that is exactly what the Parker Solar Probe has done and is doing and will continue to do as it approaches closer and closer to the Sun with each successive orbit. Eugene Parker did not have the Parker Solar Probe in mind when he wrote his 1988 nanoflare paper. He was a theorist working in an era when the instrumentation to test his ideas simply did not exist. He spent much of his career laying the theoretical groundwork, predicting the solar wind, developing the ideas about coronal heating, watching the field gradually catch up with his intuitions. He was 90 years old when the probe that now bears his name launched in August 2018, and he was there on the day of the launch. He stood on the ground at Cape Canaveral, this man who had spent 60 years thinking about the Sun's corona and the solar wind, and he watched the rocket carrying the spacecraft that would fly to the place he had been imagining for 6 decades, climb on a column of fire into the Florida dawn. He wept. Parker Solar Probe carries 5 instrument suites designed to measure exactly the things that matter for understanding coronal heating and solar wind acceleration. It measures the magnetic field directly with magnetometers precise enough to detect the fine structure of the field in the corona. It measures the solar wind plasma, the density and velocity and temperature of the protons and electrons flowing outward. It measures electric and magnetic waves, the alpha waves and other fluctuations propagating through the corona. It measures energetic particles, ions and electrons accelerated to high energies in the corona. And it measures the dust environment, the tiny grains of material orbiting close to the Sun. But the most dramatic thing Parker Solar Probe does is simply go where no spacecraft has gone before. The Alphen critical surface, the boundary that the probe first crossed in December 2021, is a fundamental landmark. Below that surface, sitting at roughly 18 to 20 solar radii from the Sun's center, the Sun's magnetic field is stronger than the kinetic energy of the solar wind flowing outward. Above it, the solar wind winds, flowing freely outward into the solar system. Below it, the Sun's magnetic field controls the plasma. Below it, you are inside the Sun's atmosphere in a meaningful, physical sense. Below that line, you are where the corona lives. And Parker Solar Probe has now crossed that line multiple times, with each orbit bringing it closer, allowing it to spend more time inside that magnetically dominated region. On December 24, 2024, the probe made its closest approach yet, 6.1 million kilometers from the Sun's visible surface, closer than any human object had ever been. The shield facing the Sun was absorbing a ferocious intensity of sunlight and radiation, but because the corona is so thin, because there are so few particles, even at that proximity, the actual thermal load on the shield was something the engineering could handle. The face of the shield reached temperatures of around 1400 degrees Celsius. The instruments sitting in the shadow of that shield, tucked into the probe's inner sanctum behind the carbon-carbon composite and the carbon foam, were operating at close to 30 degrees Celsius. Room temperature. Calmly taking data a few centimeters behind a surface hot enough to melt steel, inside a plasma of 1,000,000 degrees. This is the beautiful paradox of the mission-made physical, high temperature, low heat, the corona at 1,000,000 degrees, the shield at 1400 degrees, the instruments at 30, every step of that gradient is a reminder that temperature and heat are not the same thing, and that in a plasma thin enough to be invisible, extreme temperature does not mean extreme energy transfer. The probe is living proof of the very physics that makes the coronal heating problem strange, proving the strangeness by surviving it. And in the data streaming back from those instruments, across the enormous distance from the Sun's corona to the antennae on Earth, the mission has found something that no one had clearly seen before, something that is now at the center of the most exciting active research in solar physics. Something small and strange and potentially very important. It found the switchbacks, and that is exactly where we are going next. For now, somewhere in the data already returned in the records of the magnetic field and the plasma and the waves measured as the probe carved its way through the inner corona, the picture of what the corona is actually doing is becoming clearer. The two suspects, alpha waves and nanoflares, are no longer just theoretical proposals. They are being measured. Their fingerprints are in the data. The corona's geography, the open field holes and the closed field loops, is being mapped from the inside. And out there, in the dark, in the cold and the distance of space, the Parker Solar Probe is still going, still orbiting, still gathering, patient as mathematics, fast as almost nothing else humans have ever made. And Solar Orbiter is watching from its tilting, angling orbit, sending back images of campfires and poles and magnetic structures that no human eye has framed before. Two spacecraft launched 2 years apart, approaching the same mystery from different angles with different tools, and between them slowly assembling the full picture of what the Sun's corona actually is, why it is hot, how the heat gets there, and what the field lines kinking and snapping and waving in that bright invisible atmosphere are actually doing. The coronal heating problem is not the unsolvable mystery it once seemed. It is a problem in the process of being solved, and the solution is not one elegant answer, but something richer, a portrait of a dynamic, complex, magnetically driven environment where energy moves in more than one way, where different regions do different things, where the waves and the sparks and the currents all play their parts, where the Sun's boiling surface shakes the field lines, and the field lines carry the shaking upward, and the shaking breaks and snaps and vibrates, and somewhere in all of that, a thin and tenuous atmosphere becomes hotter than the surface below it by a factor of several hundred. We are not at the end of this story, we are somewhere in the middle, where the clues are multiplying and the picture is sharpening and the instruments are still running. And perhaps the most remarkable clue of all, the freshest, the most physically vivid, the one that may be pointing most directly to where the missing energy actually hides, is something the Parker Solar Probe found when it got close enough to see the magnetic field clearly from the inside. The field was folded, bent back on itself, kinked. And those kinks were moving, and those kinks may have been carrying the answer all along. But we will come to that in a moment, once the night is a little darker and the quiet a little deeper. If you are still here, wherever you are, with your lamp or your screen or just the dark, that is exactly right. There is no need to hold all of this at once. Let it drift. The picture of the two mechanisms, the wave and the nanoflare, the open field and the closed loop, the campfires and the probe crossing the Alphen surface in December of 2021, let it settle in gently, the way a long familiar blanket settles rather than drops. It is there even when you are not actively thinking about it. And the next part of the story, the switchbacks, the reconnection at the boundaries, the clue hiding in the kinks of the field, that part is waiting quietly ahead. There was a man who spent his career being told he was wrong. His name was Eugene Parker. And in 1958 he sat down and worked out mathematically that the Sun could not be sitting quietly in space. The corona, he reasoned, was so hot and so energetic that it could not simply end. It had to be flowing outward, constantly, in all directions, a wind made of charged particles streaming out from the Sun across the entire solar system, filling the space between the planets, reaching the Earth, reaching Mars and Jupiter and beyond, reaching the very edge of the heliosphere, where the Sun's influence finally runs out against the pressure of interstellar space. He called it the solar wind. He wrote up his theory, submitted it to the Astrophysical Journal, and waited. The paper was rejected. Twice. The reviewers told him, politely and then less politely, that the idea was absurd. Space was supposed to be empty. The Sun sat in a vacuum. There was no mechanism, they said, no reason, no justification. The solar wind simply could not exist. Parker published anyway. And a few years later, in the early 1960s, the Soviet lunar probes and the American Mariner 2 probe flew through space and measured exactly what he had predicted. The wind was there. It had always been there. It was real, and it was constant, and it filled the entire solar system, and every model of the space between the planets since then has had to account for it. Eugene Parker was right, and the field had told him he was wrong. So when NASA began designing a spacecraft specifically intended to fly close to the Sun, closer than anything had ever gone, close enough to enter the corona itself, the question of what to name it was not really a difficult one. In 2017, NASA announced that the mission would be called the Parker Solar Probe. It was the first time the agency had ever named a spacecraft after a living person. Eugene Parker was 90 years old. He attended the launch. That was on August 12, 2018 at Cape Canaveral. The rocket carrying the probe lifted off in the early hours of the morning before dawn, and Parker stood and watched it go. A man who had spent decades being told that the thing he had discovered did not exist, watching a spacecraft launch toward that thing, a spacecraft bearing his name, built to answer the deeper question his discovery had helped uncover. Parker died in 2022 at the age of 94. But by then the probe had already sent back data, already made its first close passes, already found something unexpected and beautiful and strange hiding inside the magnetic field. He knew before he died that the mission was working, that the probe was finding things, that the story was moving forward. The spacecraft itself is a small, almost delicate-looking thing, about the size of a small car. It carries 4 science instrument suites, sensors for measuring fields, waves, particles, and imaging the solar wind. And at the very front of it, like the visor of a knight, it carries a shield, the thermal protection system. It is 11.4 centimeters thick, roughly the width of a paperback novel, and it is made at its core of carbon foam, the same basic material as the carbon fiber used in racing cars and aircraft frames, but processed into an extremely light, extremely rigid foam, like the skeleton of carbon itself. The foam is sandwiched between 2 panels of carbon-carbon composite, which is a kind of reinforced carbon, where carbon fibers are woven together, and the whole thing is treated at very high temperatures until the structure becomes extraordinarily hard and extraordinarily resistant to heat. The face of the shield, the side that points toward the Sun, is coated in a white ceramic paint, because white reflects more heat than bare carbon. It sounds almost too simple for the problem it is solving, but here is what that shield has to do. When the Parker Solar Probe makes its closest approaches to the Sun, the temperature of the corona through which it is flying can reach, as you know, 1 to 3 million degrees. At the closest approach on December 24, 2024, when the probe flew just 1 million kilometers from the surface, inside the corona, closer than any spacecraft before, the face of that shield was baking at roughly 1400 degrees Celsius. Not a million degrees, not even close. And behind the shield, in the shadow it throws, the instrument sat at approximately 30 degrees Celsius, about the temperature of a warm room on a summer afternoon. That difference, The million-degree corona versus the 1500-degree shield face versus the 30-degree instruments in the shadow is not a failure of measurement. It is not a contradiction. It is the same distinction we talked about earlier, the same one that makes the corona paradoxical in the first place. The corona is hot, but it is very nearly empty. It is roughly 1 trillion times less dense than the photosphere below it. And that means that even though each individual particle in the corona is moving with extraordinary kinetic energy, there are so few particles per cubic centimeter that when they strike the surface of the shield, the total energy they deposit, the actual heat, is limited. Think of it this way. Imagine you are standing in a room and someone flicks a single burning match at you. The match is very hot. It might be at several hundred degrees on its tip. But if it goes out before it reaches you, or if it is just one match, the energy it transfers to your skin is almost nothing. Your skin is not damaged because there simply was not enough total energy in that one small match. Now imagine a different room, slightly cooler. Say, someone has lit a modest bonfire at the other end. The individual temperature is lower, but there is a lot of fire, a lot of particles, a lot of total energy flowing your way. And that room, the one with the bonfire, will do far more damage. The corona is the first room. Extremely hot particles, but very few of them. The shield face heats up to 1400 degrees, which is genuinely extraordinary. It is hotter than most things you will ever encounter in ordinary life. But it does not reach 1 million degrees because there is simply not enough material hitting it to carry that much total heat. The foam core and the carbon panels absorb what arrives, distribute it through the structure, and protect the instruments behind. The white coating reflects some of the incoming radiation from the photosphere below. The carbon does the rest. And so the instruments stay at 30 degrees, measuring, recording, sending data back across the roughly 150 million kilometers between the probe and the Earth at the speed of light, arriving 8 minutes later in mission control. It is one of the most elegant engineering solutions in the history of spaceflight. Not elegant in the sense of complicated, elegant in the sense of exactly right. A foam core, a carbon shell, a white coat of paint, and the physics of a very thin atmosphere doing the rest of the work. The probe survives not by fighting the heat, but by understanding why the heat is not as bad as it sounds. And the speed. We should talk about the speed because it is almost impossible to hold in your mind without letting it wash over you a little. The Parker Solar Probe is the fastest human-made object ever built. At its closest passes, it reaches speeds of over 690,000 kilometers per hour. That is approximately 430,000 miles per hour if you prefer that unit. At that speed, you could travel from New York to Tokyo, roughly 11,000 kilometers, in under a minute. Let that sit for a moment. Under a minute. It needs that speed because of the sun's gravity. To get close to the sun, you do not simply point and go. You need to shed the enormous orbital velocity you inherit from the Earth, the velocity that keeps the Earth itself in orbit rather than falling inward. The probe uses Venus in a series of carefully designed gravitational assists, swinging past Venus multiple times and using Venus's gravity to slow down, to shed that inherited sideways velocity, to let the sun's gravity pull the probe progressively closer with each orbit. By the time it reaches those closest passes, gravity has pulled it to extraordinary speeds. It arrives fast, and it arrives inside the corona, and it points its shield at the sun, and it measures everything it can. And among the things it measured early in the mission was something nobody had quite expected to find, or rather, something that had been seen in solar wind data before but never fully understood, never connected to the corona's interior, never traced to a specific physical process. The magnetic field near the sun was full of kinks, not metaphorical kinks, actual physical bends in the direction of the magnetic field, where the field line, which had been heading more or less radially outward from the sun, the way you would expect it to, would suddenly fold back on itself. reverse direction, flip, sometimes nearly 180 degrees, and then after a short distance flip back again to its original orientation and continue outward, as if nothing had happened. These reversals were sometimes brief and sometimes extended over large distances. They came in clusters, arriving like waves, and they were associated with jets of plasma moving faster than the surrounding solar wind. They were dynamic, moving structures. They were named switchbacks. Picture, if you can, a garden hose lying on the ground with water flowing through it from one end to the other. Now imagine that the hose develops a kink. The hose folds back on itself for a section, then unfolds and the water continues through, but its direction momentarily reverses inside the kink before continuing forward. If the hose is under pressure, that kink region might also experience a brief pulse of faster flow. The switchbacks are something like that, but in 3 dimensions, in a magnetized plasma, at the scale of a fraction of the sun's radius, moving outward with the solar wind. They are S-shaped reversals in the magnetic field, traveling as the field flows outward, creating these sudden pockets where the field direction flips and then rights itself and carries on. When Parker's solar probe first began reporting large numbers of these, the immediate question was, where do they come from? Were they being generated far out in the solar wind, some kind of turbulent folding process in the wind itself as it expanded? Or were they being created close to the sun, near the surface, and then carried outward? And if they were being created close to the sun, why? What was doing the kinking? Because if switchbacks are being created near the surface, near the coronal base, near the places where the magnetic field emerges from the photosphere into the low corona, then they are almost certainly connected to the same energy reservoirs that feed the coronal heating problem. The closer the probe got, the cleaner the answer became. There is a structure on the surface of the sun, visible in high-resolution solar images, called supergranulation. The photosphere is covered in a pattern of convection cells, regions where hot plasma rises from below, spreads outward, cools, and sinks back down at the edges. The small-scale ones are called granules, each one roughly the size of a large country, lasting minutes. The larger ones, supergranules, are each the size of a small continent and last a day or two. Together they create a kind of honeycomb of rising and falling plasma covering the entire photosphere, and at the edges of the supergranules, the boundaries of the cells, magnetic field lines from neighboring regions are swept and compressed together. In those compressed boundary zones, the magnetic field lines from different regions, which have been tangled and braided and pushed around by the constantly churning surface, are forced into close contact. And when field lines with opposite orientations are forced into contact, something happens, something physically dramatic at a very small scale. They break, they reconnect. Magnetic reconnection, as we have talked about already in this long and quiet night, is the process by which magnetic field lines that are being pushed together, lines pointing in opposite directions, snap apart and rejoin with their neighbors. The process releases energy. In the large solar flares that erupt from active regions, that energy release is enormous and violent. In the nanoflares that Parker proposed in 1988, it is tiny, a billionth of a large flare, but multiplied by countless tiny events happening constantly across the entire surface. In the coronal funnels, the specific magnetic structures that rise from the supergranule boundaries up into the low corona, like the stems of a flower opening out into the coronal volume above, the reconnection takes a particular form. Field lines that are closed, looping back down to the surface, interact at the boundaries of these funnels with field lines that are open, reaching up and out into the solar wind. The closed loop and the open field line touch and reconnect, and in doing so the open field line picks up a new kink, a switchback, and carries it outward. This process has a name: interchange reconnection. The energy and the geometry of the magnetic topology are exchanged at the boundary, and the signature of that exchange is the switchback, moving outward in the solar wind detectable by a spacecraft close enough to see it. Researchers including Justin Casper and the broader Parker Solar Probe science team worked through this interpretation in the years following the first close passes, around 2020 to 2023, building the case that the switchbacks are fingerprints. They are the marks left by the reconnection at the base of the corona. And if the reconnection there is producing switchbacks, it is also releasing energy, heat, the kind of energy that the corona needs to maintain its extraordinary temperatures. The measurements showed that the switchbacks arrive in clumps, and those clumps are associated with structures in the solar wind traced back to the supergranule boundaries and coronal funnel edges. The spatial correlation was there, the timing was there, the energy was there, at least partially. Now, to be fair and to be honest, as this night has tried to be from the beginning, the case is strong, but it is not closed. The measurements show that the energy carried by switchbacks and the Alfvén waves associated with them is, in at least some regions close to the Sun, sufficient to account for a significant fraction of the heating. But the corona is a large and varied place. Active regions with their closed loops may be heated differently from the open coronal holes that pour out the fast solar wind. The two mechanisms, wave heating and nanoflare reconnection, may divide the work between them, each dominant in the territory best suited to its physics. Quantifying the exact energy budget across the whole corona, accounting for every region and every mode, remains genuinely open. What has changed and what is important is that we are no longer guessing in the dark, we are measuring. We have a spacecraft inside the corona below the Alfvén critical surface, measuring the field directly, counting the switchbacks, tracking the waves, watching the energy flow. The data that Parker Solar Probe has returned and continues to return as it makes orbit after orbit, with each pass closer than the last, is the kind of data that turns speculation into physics. The December 24, 2024 approach, 6.1 million kilometers from the surface, is at the time of this recording the closest any spacecraft has ever come to the Sun, inside the corona, inside the magnetic domain where the field controls everything and the solar wind has not yet broken free. The probe was not just passing through the outer corona the way you might dip a hand into warm water. It was deep inside the structure, in the region where the heating is actually happening, in the low and middle corona, measuring the very field reversals and plasma jets that may be the mechanism. And each pass, the orbit is slightly different, slightly closer, slightly revealing. The data accumulates, the models are tested against it, the picture sharpens. There is something else worth holding on to as we near the end of this journey, something about the shape of the whole problem, the way the pieces fit together. Eugene Parker predicted the solar wind in 1958 because the corona was so hot. The heat was the reason the wind had to exist. If the corona were cooler, the particles would not have enough energy to escape the sun's gravity, and space near the sun would be a quieter, emptier place. The solar wind blows because the corona blazes. So the coronal heating problem and the solar wind mystery are not two separate puzzles. They are the same puzzle, seen from different angles. What heats the corona also drives the solar wind. What drives the solar wind is the overflow of whatever is heating the corona. The switchbacks found by the Parker Solar Probe, the candidate fingerprints of interchange reconnection, are not just a potential explanation for why the corona is hot. They are potentially the same mechanism that energizes the wind, that fills the heliosphere, that reaches the Earth and shapes the magnetosphere, that produces the auroras that glow at the poles on certain winter nights. It is the same energy, the same process, running from the tiny scale of magnetic reconnection at the supergranule boundary, where field lines the width of a few hundred kilometers interact, all the way out to the scale of the entire solar system, where the wind finally stops. Parker, when he was old and being asked about the mission and what it meant to him, was characteristically understated. He had spent his career looking at the large-scale consequences of processes he could only model mathematically. He had predicted the solar wind without seeing it. He had proposed, through his nanoflare theory, that the corona was being heated by tiny, invisible reconnection events, too small to detect individually. And now a spacecraft with his name on it was flying through the corona, finding the signatures of exactly those reconnection events, bringing home the data that would finally let the theorists and the observers sit at the same table and check their work against each other. The oldest unsolved problems in solar physics have a way of being solved by getting closer. Not conceptually closer, but physically, literally. The eclipse observers of the 19th and early 20th centuries had to wait for the moon to block the sun before they could see the corona at all. Walter Grotrian and Bengt Edlén had to wait for laboratory spectroscopy to advance far enough to identify what iron stripped of 9 to 13 electrons would emit. Eugene Parker had to wait for Mariner 2 to fly through the space between Earth and Venus and measure what no instrument had reached before. And now we have a spacecraft that crosses the Alphen surface, that enters the corona, that reads the magnetic field at the place where the heating is occurring, that sends the data home 8 minutes later at the speed of light. The distance between the question and the answer has never been smaller, not closed, but smaller, and it is shrinking orbit by orbit. There is a particular image that has stayed with me in thinking about all of this, and I want to leave it with you as you settle into whatever quiet you have found tonight. The sun right now is doing what it has done for roughly 4.5 billion years. The photosphere is churning in its convection cells, the granules rising and falling in their minutes-long lives, the supergranules turning over in their days-long cycles, the magnetic field being swept and braided and compressed at the boundaries. Somewhere in that churning, reconnection is happening at this very moment. Field lines are snapping and rejoining. Energy is being released in tiny bursts, far too small to see from this distance, far too small to notice against the roaring backdrop of the surface. But above the surface, in the transition region, that razor-thin layer a few hundred kilometers thick, where the temperature rockets from 20,000 degrees to over 1 million, that released energy is arriving. Waves are breaking, the thin plasma is absorbing the energy, the ions are accelerating, and the corona, that extraordinary tenuous shimmer of million-degree gas, is being maintained against the darkness that surrounds it, held at its impossible temperature by a constant, tiny, invisible rain of magnetic events that no human eye will ever see directly. And inside that corona, right now, the Parker Solar Probe is flying, carrying its shield of carbon foam and carbon-carbon composite and white ceramic paint tilted precisely to keep the instruments in shadow, sending pulses of data back across 150 million kilometers at the speed of light. Its instruments are at 30 degrees, the corona around it is 1 million. It is perhaps the most extreme version of what science does at its best. We build a thing as small and careful and specific as we can make it, and we send it to the place where the question lives, and we ask the question from the inside. And the answer comes back, slowly, in data packets and analysis papers and revised models and conferences where people argue about what the measurements mean. And gradually, through all of that, the picture sharpens. Not all the way, not yet. The two mechanisms, wave heating and nanoflare reconnection, are both real, both operating, both leaving their marks in the data. The exact fraction each contributes, the exact way they vary from region to region, from the quiet sun to the active regions to the coronal holes that breathe out the fast solar wind, that is still being worked out. The switchbacks are strong candidates for interchange reconnection near the coronal funnel bases, and the energy they carry is, in some regions, enough to matter. Whether they account for the full budget of coronal heating, or whether they are one thread in a larger tapestry of mechanisms, the data will decide. But the data exists now. It is real. It has been measured from the inside. That is the part of this story that I think is so easy to miss when the coronal heating problem is described as simply baffling, simply unsolved, simply a mystery science cannot crack. Because it is not a stalemate, it is a detective story in its final chapters. The suspects have been identified. The weapon, magnetic energy released at the boundary between open and closed field lines, is in evidence. The motive, the thermodynamic impossibility of simple conduction through a layered solar atmosphere, was established in the 1940s, and the detective, a small carbon-shielded spacecraft moving at 690,000 kilometers per hour, is still on the scene, still taking notes, still sending them home. We are lucky, in a strange way, to be living in this particular moment. The question has been open since Grotrian looked at that green line in 1939 and knew something was wrong with the picture. It has been open for longer than most living people have been alive, and within the last decade, for the first time, we have the instruments to probe it from the inside. That is not nothing. That is, in the slow pace of science as it is actually done, something close to extraordinary. So, wherever you are tonight, in your bed or on your couch or somewhere quiet with the dark settling around you, you now carry something that very few people in human history have carried. Not the complete answer. The complete answer is not quite in anyone's hands yet, but the shape of the question and the shape of the progress. The campfire inversion that is not an inversion, but a separate energy source. The razor-thin transition region where the temperature leaps by a factor of 50 in the space of a few hundred kilometers. The invisible nano-flares snapping like tiny sparks across the magnetic web. The Alfvén waves traveling upward like vibrations along a plucked string. The switchbacks folding and unfolding in the low corona, carrying the fingerprints of reconnection at the base of the coronal funnels. The carbon shield holding at 1,400 degrees, while the instruments behind it stay warm and calm and measuring. The green line that was not a new element, but the signature of iron so thoroughly stripped of its electrons that it required 1,000,000 degrees to exist. Bengt Edlén, in 1941, working at his laboratory identifying that line, understanding for the first time that the sun's outermost atmosphere was doing something that should have been impossible. He could not have imagined that 80 years later a spacecraft would be flying through that impossible atmosphere and measuring the magnetic kinks that might explain it. The distance from the question to the answer at the scale of human lifetimes is not so large. Eugene Parker, who was told the solar wind could not exist, who lived to see a spacecraft cross the surface he had spent his life studying from a distance, who heard the data coming back from inside the corona. He knew something about the relationship between patience and correctness, about holding a position long enough for the instruments to catch up to the theory. The sun does not know any of this. It will keep churning and braiding and reconnecting and emitting its impossible corona for another 5 billion years or so, long after anything built by human hands has been recycled back into stardust. The coronal heating is not for us. It is not a performance. It is simply what a star does when it is this massive and this magnetic and this old. It is physics running the way physics runs, indifferent to whether it is understood. But we are the kind of thing that notices. We are the kind of thing that looks at a green line in a spectrum and asks, what is making that? We are the kind of thing that builds a probe out of carbon foam and ceramic paint and sends it into a 1,000,000-degree atmosphere to find out. That impulse and the noticing, the asking, the building is not separate from the universe. It is the universe doing something it apparently does when conditions are right, making creatures that look back at it. You are one of those creatures, and right now, wherever you are, wherever you have settled for this night, you are made of the same atoms that the sun is fusing, the same iron that the corona ionizes so thoroughly. When the instruments on the Parker Solar Probe measure iron atoms stripped of 13 electrons glowing at 2 million degrees, they are measuring the same element that runs through your blood right now, the same periodic table entry, the same nucleus with 26 protons at its center. The corona is not foreign to you, it is a different arrangement of the same stuff, a wilder, hotter, more extreme arrangement, but the same stuff. The sun's surface is 500 degrees and its corona is 1,000,000 degrees, and that fact has been unexplained for more than 80 years. And it is being explained right now, incrementally, orbit by orbit, data packet by data packet. And you spent this night listening to the story of how. That is a good thing to carry into sleep. Not the whole answer. There is no whole answer yet to carry. But the shape of the question and the shape of the progress and the knowledge that the question is not open because no one has tried, but because the universe is genuinely delightfully complicated, and because sometimes the right instrument takes decades to build. At the start of this night, I asked where you are, where in the world you are, and what time it is in your corner of the dark. And I hope that question is still somewhere at the edge of your awareness, because I want to come back to it now, at the end. Wherever you are, whether it is midnight or 3 in the morning, or the quiet hours before dawn, whether you are in a city with streetlights glowing orange outside your window, or somewhere rural with nothing between you and the sky, the sun is out there, on the other side of the earth, or rising toward you, or overhead, if you have drifted through a long day into this. And surrounding its surface in a thin and tenuous halo that no human eye can see except in the brief totality of an eclipse is the corona. Right now, 1,000,000 degrees, being heated by mechanisms that scientists are still measuring, still debating, still refining. The Parker Solar Probe is out there too, somewhere in its orbit around the sun, cycling inward and outward, making its periodic close passes, sending its data home. The question is open and the instruments are running and the night is quiet, and you have heard the whole long, strange, beautiful story of it. If you enjoyed this slow journey into the sun's most extreme and mysterious layer, a gentle like or subscribe to Nightwatch Observer would mean a great deal. Small creators like me rely on your support to keep these nights going. And if you would like to leave a word before you drift off, I would love to know where you are listening from tonight and what time it is in your corner of the world. A city name, a time zone, a simple good night. Any of it is welcome. The Night Watch has the dark covered. You can let go now.